Good evening, everybody. My name's Mark Hoffman. I'm Dean of Engineering here at UNSW, and I'm very pleased to welcome you to the Pollock lecture. We're very proud to host this together with the Royal Society, and I'd like to give a particular welcome to the immediate past president of the Royal Society, Bryn Hibbert, and also Herma Butner from the Royal Society. I'd just like to, of course, we have our speaker, Andrea Morello, and I'd also like to welcome Andrea's colleagues. I noticed Jared up the back there. I'd like to welcome Michelle Simmons, who's also Australian of the Year, but she's here tonight because she's Andrea's colleague. But before we go any further, I'd like to acknowledge the Bedegal people, who are the... pay respects to elders past and present, and extend that welcome to other Aboriginals present. Now, as I said, we're particularly proud to host this event with the Royal Society. UNSW has as its philosophy to be an outward-reaching university. And we're also very proud and try to make sure that we're considered a partner of choice. Now, to become a partner of this event, you have to employ the winner. But we're also very proud that the Society had the foresight and was enlightened enough to regularly award this lecture prize to a UNSW staff member. Now, one of the reasons where is we have many brilliant researchers, and research and great researchers are really important to universities. But as we all know, it's one thing to do great research, but for the community and society, that research really needs to be communicated to be really important and really effective. Now, one area where we do great research is in the area of quantum computing. I had the pleasure this morning with a number of other people in the room to witness the signing of an MOU between Silicon Quantum Computing, which is the major offshoot of quantum computing in UNSW, and CEA, a French organisation with collaboration. And that MOU was signed in the presence of Emmanuel Macron and Malcolm Turnbull. So we can just see the level of international significance of the work that's happening. Now, of course, this research has to be communicated. And some of you may remember about 2 years ago, Justin Trudeau made himself, sort of got a little bit of fame for himself by successfully, what people said, explaining what quantum computing was all about. Now, my view is that Justin Trudeau had actually managed to do this by watching Andrea Morello's YouTube videos. But he didn't do such a good job. So what that meant to me is that obviously Andrea Morello is a great science communicator about quantum computing, and he's probably preparing himself to be a president of a G20 nation. And I think he would do a great job. However, to introduce Andrea, I'd like to call to the stage Bryn Hibbert.
Thank you. Well, hello everybody. I'm Bryn Hibbert, the immediate past president of the Royal Society of New South Wales. I've got this patter off really good. I've been president for 2 years, and Ian Sloan, also at UNSW. In fact, I should say that at one of our meetings, it was suggested by one of my colleagues on the council that he said, "This isn't the Royal Society of the University of New South Wales," he said, as we just inducted our umpteenth fellow from this institution. And indeed, Sydney University makes up the numbers very well, I should say. The Royal Society of New South Wales claims, and in fact I think is, the oldest learned academy, as it were, in the Southern Hemisphere. Okay, Antarctic and bits of South America, but oldest. We kick off in 1821 as the Australian Philosophical Society, and our remit, as you can see on our banner over there and at the bottom, is the encouragement of studies and investigation into science, art, literature and philosophy. And so we're a child of the Enlightenment. Thomas Brisbane was our first president, and so we hail from the Royal Society of Edinburgh rather than the Royal Society of London. And that actually has made quite a big difference. So we knock around for a long time. In 1866, we get the title Royal Society. And although we're all Republicans to a man or woman, it's rather nice being the president of the Royal Society of New South Wales. So we go on, and for a long time, you see, we start off as being the only game in town. If you want to know what Mr. Darwin's thought of this week, you've got to go to the Royal Society of New South Wales to find out. But then over the years, of course, everything else happens, and there are other societies, and science gets its act together, as it were. But in recent years, we've suddenly had a resurgence because this Enlightenment value of a kind of holistic view of our problems of society, which are solved by science, but implemented by art, philosophy, and literature, suddenly makes a lot of sense. And so the Royal Society is burgeoning. And indeed, if you're not already a member, we have many fellows and members in the audience today, then please think of joining. I'd like to welcome Michelle Simmons, who's one of our distinguished fellows, along with a whole bunch of Nobel Prize winners and other ne'er-do-wells. So if I can go on to dear old James Arthur Pollock. I noticed Andrea has called his lecture his memorial lecture. I mean, yes, he's dead, but then so are a lot of people. So we just call it the Pollock lecture. So over the years, we've had a whole bunch of seriously good prizes to win, and this one in physics. And I think Andrea is going to introduce his talk by saying a little bit more about the physics of James Pollock. But I thought I'd just say who else has won the Pollock lectureship. And you can see, indeed, Michelle Simmons managed it in 2013, Brian Schmidt, Nobel Prize winner, 2009. We're still trying to work out whether the Josephson in 2006 was the Josephson or not. But keep going back, and you come to Fred Hoyle, the astronomer, Massey, of course, and Harold Jeffreys. Some people will have heard of. So I think I'm saying that this is a terribly prestigious thing to have, and should go really well in your CV, or not. So. It's my very happy duty to introduce Andrea. The usual thing is that I now read out what he's done for his entire life, but other than coming from some small town in Italy that bears his name, there's a big jump to the point where he is now a really serious player in this game of quantum computing. He gave the Royal Society an actually fantastic lecture last year, after which I said, I've heard many people give lectures, actually including Michelle Simmons, and the cumulative effect has suddenly, I think I nearly have got it, except that I'd just like to hear it once more, just to make sure that I know what we're doing. Andrea was one of the two speakers in our last year's programme that the Governor of New South Wales decided he'd like to hear more of. So in fact in February he wandered down to Andrea's labs for a quick tour. And he's terribly good at this. So I managed to get biffed off, so there was no president of the Royal Society, there was no Ian Jacobs, there was no even Dean of Engineering or Science, but here was the Governor thinking, I'd like to know more about this, and he rocks up and Andrea tells him all about it. That's kind of nice, I think. So, Andrea is going to tell us about, what was it again?
Engineering for understanding. So it's not just quantum computing, there's going to be a lot more. Thank you.
What more can I say?
Thank you, Brian.
Okay. Thank you all for coming along tonight. I'm going to have to use this sort of rock star style microphone that is not quite rock they have outside, but it was a bit of a beat. So I'm going to have to try and go to the beat of some good dancing music because there's a lot of things I want to tell you about tonight. So as I was saying, the broad title is Engineering for Understanding. So this is not going to be a talk just about quantum computing. I will mention that, but it's not the main plate. Okay, I want to do something actually bigger than that. But before I get into that, I feel like I have some duty to acknowledge and recognize the legacy of Professor James Pollock. And so I did a bit of research on him. There isn't a lot about him. He passed away in 1922, so it's a long time ago. He never did any work on quantum mechanics. His main interest was actually in ions and electrical discharges. But I found a nice obituary about him in Nature, in fact, in 1922. There's a couple of sentences that stood out, and they sort of matched the theme of the night. Whatever the apparatus was, the best result must be got out of it. His skill in adjusting instruments has probably never been equaled. And he allowed his scientific imagination more scope than usual. So these are attitudes that will become recurrent in the talk that I will give tonight. Because tonight I will tell you about how we, first of all, imagine and then design and build and fine-tune artificial pieces of devices and quantum objects that behave in a way to exploit the properties of quantum mechanics. So the menu for the night is, first of all, some basics of quantum mechanics. I'm not the kind of person who goes around saying, oh, quantum is weird, you'll never understand it, so I'll just show you some pictures and just be content with that. No, it's not like that. There will be a lot of pictures, but I will try to give you some sense of what it is that we're talking about and why it matters and how it changes the way we can operate certain devices. And then I'll go into devices themselves. So I'm going to tell you something about the things we do here in my group at UNSW, which is a platform for making quantum bits in silicon using individual dopant atoms. Then I'll say a few words about quantum computers, actually not very much, because then I want to tell you something about my latest and greatest love, which is quantum chaos. Quantum chaos is more important than people realize. It has been a somewhat dormant discipline for maybe 2 decades, but now there is a huge resurgence in the interest in quantum chaos for reasons that I will try to explain. Okay, so let's start with some basics of quantum mechanics. Quantum mechanics is the description of the world that stems from essentially a new law of nature, which is called the Heisenberg uncertainty principle. The Heisenberg uncertainty principle says that if you are trying to determine the position and the momentum, which is the mass times the velocity of some physical object, you cannot do that with absolute precision. The product of the uncertainty on the two, let's say, observations of position and momentum must be larger than half this physical constant that's called the Planck's constant, that has this value of 1.05 times 10 to the minus 34 joules second. Now, I don't expect you to have an immediate tangible sense of what that number means. So I'm going to give you an example. Take a tennis ball that goes at 30 meters per second. Let's say you're an amateur tennis player, you hit it at 100 kilometers an hour. So the Heisenberg uncertainty principle tells you that if you want to know its velocity to within 17 significant digits, you need to give up your ability to know where it is to better than 10 to the minus 17 meters, which is essentially billions of 10 nanometers, which is actually less than the size of a proton. So the reason I'm giving you this example is to say that for a tennis ball, quantum mechanics doesn't matter. It's completely irrelevant at this scale. Now take an electron instead at the same speed. Now, the electron is much lighter than a tennis ball, so this mass that goes into this factor for the momentum is, of course, many, many, many times smaller. So for an electron at the same speed, if you want to know its velocity to within 30%, to within 10 meters per second out of 30 meters per second, you need to allow an uncertainty on its position of 10 microns, which is the thickness of a human hair, and many, many orders of magnitude bigger than what people think of as the size of the electron. So what that means is that you don't know where it is and you don't know how fast it goes. So for a particle the size of an electron, the Heisenberg uncertainty principle completely rules the dynamic. It changes the rules of the book of how you even think of such an object. I should mention, this is not a statement on our ability to observe the world. It's not like, oh, I make a better instrument, I'm going to improve on that. This is a new law of nature. It's got nothing to do with humanity, of our capacity to do anything. It's a new law of nature, like a Maxwell's equation. Okay? Now, think of this electron, which you vaguely know how fast it goes and kind of more or less which way it points, and you should think of it really as a wave of probabilities, like a blob of probability that it's more or less there, going more or less in that direction, okay? And you shoot it towards a screen that has two slits. Now, you can't talk about the trajectory of the electron. That electron is not like a bullet. It's a wave of probability. And in fact, depending on how you design the slit, this wave might be delocalized over both apertures. So in fact, the electron passes through both of them. We say it's in a superposition of going to the left and going to the right. And you know that that is the case because if you look at the pattern of finding, imagine you shoot electrons one after the other, and you look behind the screen and you look at where the pattern of finding electrons is, you don't see two lines behind each one of the apertures. You see an interference pattern as you find for waves, like electromagnetic waves or even water waves. And so this really tells you that the electron is a wave of probability that can be spread out in space. And so if you really insist to think of it as a particle, it's a particle that is in a superposition of having gone to the left and having gone to the right. At which point, people go all bananas and say, oh, you know, this quantum is weird and all this nonsense. This is complete nonsense. All right, I'll get to that in a moment. Anyway, before I get to the nonsense or the non-nonsense of quantum superposition, so I've shown you that a tennis ball is not a quantum object, an electron is a quantum object, but there is a big gap in size and mass between these two. So where do you draw the line? Where does something stop being quantum and start being classical? Well, it turns out people have done this kind of interference experiments with two slits, something more complicated than that, but the same idea, with molecules as big as this one. This is carbon 168, hydrogen 94, fluorine 152, oxygen 8, nitrogen 4, sulfur 4. It's probably got a name that I can't remember. Anyway, it's a big molecule. So this has been seen to behave like a wave and to be in a superposition of going through the left and going through the right. Now, you say, okay, it's a big molecule, but it's still small on the grand scale of things. This is the smallest virus known. It's called the porcine circovirus. It's a virus that affects pigs. And so on that scale, that's how big it is. Now, a virus is not quite a living cell. If there's any biologist in the room, please don't shoot me down. But it's on its way to being a living organism. And so you can imagine you're not a long way away from being able to put a virus, which is almost a living organism, in a quantum superposition of being in two places at the same time. So that starts to be kind of fascinating when you think about it. Now, this is another object. This is a completely artificial object. It's an electronic circuit made out of superconducting metal. This was studied already 15 years ago. Pioneering work was done in the Netherlands. This is an electronic circuit that people have seen a quantum superposition of an electrical current flowing clockwise and flowing counterclockwise. This is not the same as saying there is zero current. It's not. It's a sizable current flowing one way, superimposed with flowing the other way. So it flows both ways at the same time. Now, this thing is almost visible on the naked eye. On this scale, that's a human hair. Okay? So if you're a bit short-sighted, you can probably see it with your eyes. If you're not short-sighted, you take a trivial magnifying glass and you'll see it. Okay? So the whole narrative of quantum is small and classical is big is already falling apart. I mean, we're already pushing this boundary way up. And in fact, this will be a recurrent theme of my talk tonight. The deep understanding of how and why quantum dynamics turns into classical dynamics is still an open question, and I will get back to this in a moment. Now, let me get back again to superposition. Is it weird? Is it odd that an object can be in two places at the same time? Now, I've been working on these things for 20 years now, and to me, what is weird is that people don't find it obvious. Because think of this example. Think of two protons, okay? Two positive charges and one electron. So this is like two hydrogen atoms that have been ionized, and then you give them one electron back. Now, your classical intuition tells you, well, that electron could belong to the left hydrogen atom, or it could belong to the right hydrogen atom. Now, how does it choose? Those two protons are exactly identical. What makes it choose one or the other? I mean, the logical, natural answer is, well, nothing. He doesn't choose. He orbits around both. He's in a quantum superposition of being on the left proton and on the right proton. That is the logical answer, not the weird idea, oh, it's on the left or on the right. That actually makes no sense when you think about it. And so all the, chemical bonds, when you have a covalent bond, there are electrons that are spread across, more than one atom, and that's what holds them together. Now, this is a special case where there is a particle that has, let's say, in its simplest form, two basic choices, left or right. Now, as you all know, all of the modern information era is predicated upon digital data. Digital means it's encoded in binary numbers of the form 0 and 1. So when you have a physical system like this that can have two basic configurations, left or right, you could say, well, I could call the electron on the left a 0 and the electron on the right a 1. So now I have a digital bit, right? Maybe I can use it to encode information on it. The difference here is that you also have this situation where the electron is spread across two. In fact, that's the natural situation. So how do you call that? Is that a 0 or a 1? Well, it's a quantum superposition of 0 and 1. And that's completely normal. This is called a charge qubit. Qubit stands for quantum bit, and this is one where the physical object that carries the information is the charge of an electron. Now, there's something interesting that happens here. Because this superposition state is in fact the natural lowest energy state, if you tried by some means to pull the electron and force it to be on one side, what actually happens is that it doesn't want to stay there. It oscillates between the two. These are quantum oscillations, and when this happens, if you look at it, you got two positive charges and one negative charge that jumps left and right. This is like an oscillating electric dipole, so this thing actually radiates. It radiates an oscillating electric field, which can be of use for certain things. Another way to make a quantum bit, which is my favorite way and that of many other people, including in this room, is to use another quantum two-level system that's called the spin. The spin is another fundamental, property of microscopic particle. Every electron, every neutron, every proton has a spin. And if it's a spin with a quantum number of 1/2, it has two basis states. So the spin is like, you can think of it as a mini needle of a compass, like a tiny magnet at the subatomic scale that produces a tiny magnetic field. So now you can call the 0 logical 0 state the spin pointing down, and the 1 the spin pointing up, for example. You can also here make a quantum superposition of up and down, which kind of pictorially you can think of as the spin pointing horizontally, but it's a bit more complicated than that. Now, in this specific case, the stable configurations of the spin are actually the up and down. The superposition is the non-conserved one. And so if you place it in a superposition, it will start to oscillate. In fact, it will start to precess like a gyroscope. And so this again will radiate a magnetic field that oscillates in time. Now imagine having billions and billions of these spins that all oscillate like this and all radiate this oscillating magnetic field, all in sync. This could be enough of an oscillating magnetic field for you to actually pick it up with a pickup coil. And in fact, if you've ever had the disgrace of needing to go to hospital to get an MRI, that's exactly what happens in your body. So if you've been in an MRI machine, what happened inside of you is that the proton spins inside some volumes of your body have been put in a quantum superposition of up and down and then left to oscillate so that they radiate out an oscillating magnetic field that is then picked up by some pickup coils. And then with this, the doctors can reconstruct these three-dimensional images, sections of your body, without having to slice your head in half, right? So it's very convenient. This is reality. This is not science fiction. There's nothing weird about it. Now, I was a little careful, as you may have noticed before, saying if you have billions and billions of these spins, you can see this oscillating magnetic field. But what happens if you have only one? Now, if you read the textbooks of quantum mechanics, they will talk about what's called the quantum measurement postulate that describes what happens when you try to observe a quantum system. And the postulate is composed of a few components. First of all, if you have a quantum system that is in a superposition state, and you measure it along a certain direction, for example, let's say you want to know what is the projection of the spin, think of it as an arrow, like a compass, what is the projection along the north-south axis, okay? Now, the postulate of measurement tells you that the outcome of the measurement can only be one of what's called the eigenvalues, which means the natural values of the system. So it can only be up or down. You will never see it pointing horizontally if you measure it vertically. This is what's in the books, okay? Secondly, the outcome is random. If it's in an initial superposition, equal superposition of up and down, you can never predict which way it comes out. You can only tell the probability, which is if it's an equal superposition, will be 50% up and 50% down. And then there's the final trouble spot, which is that the measurement apparatus is classical. So if I were to try to justify to you this part, I would probably look like this. Because as I was showing to you 3 slides ago, where is the boundary? What's quantum and what's classical? Is it classical because it's big? Is it classical what? So the quantum measurement postulate, as you see it in the books, actually hides a very profound question, which is, what is it really that constitutes a measurement? And at what point is there an irreversibility, we call it a non-unitarity, for those of you who know what that means, of the dynamics of the quantum system? Where does it happen and why? We actually don't really know this yet. And one of the things that I would like to contribute to quantum physics is maybe a little help on figuring this out. Okay? All right, so next chapter is how to do something about it. Let's build some quantum devices, okay? So I've given you all the sort of, not all of it, some snippets of theory behind it. Now let's move on and do something about it, okay? So what we do here at UNSW, and we are rather famous in the world for this, is we build quantum devices that are made out of silicon, which is the same material on which all of your classical computer chips and mobile phone, they're all built on silicon nanoscale transistor. And then we place inside of silicon a different atom, which is phosphorus. So you see, silicon is here on the periodic table. Phosphorus is just one step to the right of silicon. So if you replace a silicon atom with a phosphorus atom, that phosphorus atom has an extra positive charge that is not compensated by all the bonds to the rest of the silicon atoms in the crystal. So what happens is that this extra positive charge itself will bind an extra electron. So this looks a lot, in fact, like a hydrogen atom almost, but it's like a hydrogen atom in a solid crystal. And in fact, the analogy goes further because so you have this electron, which has itself a spin of quantum number 1/2, but phosphorus also, just like hydrogen, has also a nuclear spin 1/2. So in fact, a phosphorus atom is a 2-qubit system. There is an electron spin quantum bit, and there is a nuclear spin quantum bit that are coupled together by some magnetic interaction. It's called a hyperfine interaction. Now, what we normally do is that we place this device in a strong magnetic field that we make with a superconducting magnet. And when you do so, you will get 4 sort of stable configurations, which are basically all the combinations of electron down, nucleus up. So the lowest energy configuration is electron down, nucleus up, then there's down, down, then there's up, down, and then up, up, okay? And then remember what I was telling you before about this oscillating magnetic field that the spin radiates when you put it in a superposition? This thing oscillates at a very specific frequency, which is in fact given by the energy difference between the two basis states divided by the Planck constant. Now, the process also works in reverse. So if you apply an oscillating magnetic field to the spin at the appropriate frequency, you can actually flip it from down to up and back. You can actually make it go excite and de-excite if you hit the right frequency. So here we got 4 possible frequencies. There is a frequency to flip the electron when the nuclear spin is pointing down. There is another one to flip the electron when the nuclear spin is pointing up. So this is what you do to make an electron spin qubit. And then there's going to be a frequency to flip the nucleus when the electron is up, and a different one to flip the nucleus when the electron is down. So this is the nuclear qubit, okay? So we got 4 frequencies, which if we irradiate the atom with those frequencies, we can actually manipulate the direction of that single spin, be it the electron or the nucleus. So to do that, and I mean, doing this is actually not that complicated. Irradiating an atom with microwaves is not that hard in itself. The hard thing is to measure it, okay? So to measure a single spin, we had to, do some very hardcore nanoelectronics. But at the end of the day, the way we do it in my group is a modification of the standard techniques that are used to make ordinary computer chips. So it's silicon, a silicon oxide insulator, and some metallic electrodes on the top. Okay, so it's not a big departure from the way ordinary computers are built anyway. So let's say we have a phosphorus atom here, which is introduced by ion implantation. Then we fabricate a transistor next to it. This is a bit of a special transistor, but I won't go into that. It's a very non-linear transistor that switches between on and off at the movement of a single charge. It's very sensitive. And then the yellow one here, this is false colored, of course, is a microwave antenna that irradiates with an oscillating magnetic field to control the spin. Okay? So this is, let me just highlight the scale here. This is 500 nanometers, so half a micron. So this transistor here is about 100 nanometers across. So to give you a sense, let's say from end to end of this transistor, there might be, 400 silicon atoms. So this is small. But then again, what you've got in your mobile phone is just this small. So it's just the size of modern nanoelectronics, okay? So it's hard, but it's not amazing in itself. This thing itself is just a zoom in of the actual chip. So this is just taken under a microscope. The chip, so this is one device, and it's 1.2 by 1.2 millimeters. So it's a small square. This you can actually see with your naked eye. And then the thing is connected to a printed circuit board, which itself gets bolted onto this giant machine. This thing is about 2.5 meters tall, 3 meters long, 1.5 meters wide. And then once you close it all up and turn on those 15 kilowatts compressors at the back, this thing goes to 0.01 degrees above absolute zero. So this chip gets cooled down to nearly absolute zero temperature for the purpose of eliminating any spurious interaction with the outside world that may scramble the delicate quantum states that we want to prepare. All right, so this is now a movie that's been made, in fact, by a student of UNSW at the College of Fine Arts a few years ago. It's quite accurate, actually. We sat down with the students and really said, okay, this is the way it actually works. It's quite realistic. So imagine so this little red dot here is the phosphorus atom that we have placed inside the chip. So imagine you are inside of the silicon chip, and you're looking up at the ceiling. So that's the top of the chip up there. And as you look up, you see this is the transistor. These gray lines are the metallic electrodes that define the transistor. And the blue spheres are the electrons that are pulled under the gates by the voltages you apply to these electrodes. And then what you see here, this is the tip of that microwave antenna for irradiating the spin. So the way this works is the following. You start with a transistor in a state where it doesn't conduct electricity. So the current is zero. And that is always the case when the atom is ionized. You see, I haven't put any blue sphere around this. That means that that electron that normally likes to sit on that phosphorus atom has been ripped away. Now I let an electron come back on it from this island of electrons here, and it will always come on spin down for reasons I won't explain. And then I radiate it at the correct frequency given the orientation of the nuclear spin. Now this electron starts to rotate up, and when it's pointing up, it can then escape again. And when it escapes, it disgorges a current through the transistor. Then after a while, another electron will go back on the atom and will freeze the current again. Now I can switch frequency to the frequency that it would have if the nucleus had turned. But if the nucleus didn't change, then nothing happened. The electron cannot escape and the current doesn't flow. So this is a lot of blah blah. Now let me show you what you actually see in the lab when you do this. Let's see if this thing runs. Please don't freeze on me. Okay. So this is what you see on the screen of the oscilloscope that is connected to an amplifier that amplifies the current going through the transistor, okay? So when you see the flat line there, it means zero current. So there's zero current for a bit, and now you'll see in a little while, let's see when it happens, boom. Now you see all these spikes of current. That happens when you hit the right frequency. So that electron starts spin down, gets flipped up, escapes, unblocks the current, then the current stops again, and then you do it over and over again. So this is when you see spin up electrons coming out all the time. Then you see at some point it stops. Why did it stop? It stopped because we irradiated the nucleus and we flipped it the other way. So if the nucleus turns the other way, now the electron doesn't respond anymore. So now you see flat current. And then we flip it back. So I want you to ponder this for a minute, okay? What you are looking at, and there's no trick, this is just what you would see if you came to the lab. You are watching, in real time, the quantum state of a single electron spin. Every time you see a spike, it's an electron spin up. You're also watching, in real time, the quantum state of a single nuclear spin, the nucleus of an atom. Because whether or not there's a lot of spikes, or no spikes, like it will happen in a second, depends on the orientation of the nucleus. This is the sort of thing that 20 years ago, my quantum mechanics lecturer told me could not be done. In the old books, you'll say you can never think of a single quantum system. You always have to think of ensembles of systems. Now we do it every day. So this is one way in which our engineering ability to create devices like this and operate them to this level of precision has given us a window on the quantum world that I was taught not even a century ago, 20 years ago, just could never be done. Okay? This is a novelty. This is a technical novelty that has impact on the understanding of quantum mechanics. Now, this is an experiment where we start with the electron pointing down, and then we irradiate it for longer and longer times. And you see this is a nice, fast sinusoid. So what this is showing is that the electron starts down and then goes up and back down and up and back down and up and back down over and over and over again. So in the language of quantum computing and digital quantum bit, when it's down here, it's a logical 0. When it's up there, it's a 1. But you see, we also have points that are halfway. But to collect those points, we need to take statistics. Remember what I told you about the quantum measurement postulate? You can never see it anywhere other than up or down. But once you've made it in a superposition of up and down, and you repeat the measurement, let's say 100 times, you will see 50 times up and 50 times down. And so then we take the average of that and we give us 0.5. That's how we get these points in the middle. On a single shot, we can only ever see up or down. Okay? Now, it's a technicality, but it's actually very important. Let's say you make a quantum superposition. This thing then starts to oscillate. How well defined is that oscillation? If we want to encode quantum information into the state of this spin that oscillates, we need to keep track of that oscillation. So if the speed of oscillation changes in time, takes a random component, then we lose track of it. It's like a clock whose quartz oscillator starts to oscillate at random frequency, it just goes out of time. So this measurement shows that for the electron spin, you can keep track of that up to about half a second. For the nuclear spin, you can keep track of it up to about half a minute. Now, this is an eternity in the quantum world. It is truly an eternity in the scale of quantum phenomena. And this is not an atom in vacuum held by a laser in a vacuum chamber. This is a phosphorus atom in a functional, man-made silicon electronic device. Okay? This is actually mind-boggling, and it's still, I think, the record for quantum memory time in the solid state. All right, one more thing that I didn't want to talk about in the introduction to quantum mechanics. I'll introduce it now because it has to do with some of the measurements we've done, is entanglement. You probably heard of it a number of times in the popular media. So if you have, now take two spins, okay? Everything I told you so far was about one spin. Now take two. And there are some very fundamental, very natural forms of interactions between spins, for example, that make them want to point anti-parallel to each other. They don't care which way they point. They just have to be opposite to each other. So now, again, don't let your classical intuition, quote unquote, fool you. It doesn't mean that they're either up-down or down-up. Because any other configuration, as long as they're parallel, is just as good. So then what is the logical, natural, intuitive, natural state of two spins that want to point anti-parallel? Well, it's a quantum superposition of them being up-down and down-up. There's nothing weird about it. It's actually completely logical. There's no reason to choose one over the other, so you don't choose. You take both. So if you have two spin, it turns out we have four sort of basis states, two of which are entangled states. The other two are trivial, up, up, and down, down. But they have higher energy than these ones. Now, if you now think of this, you see I've kept the notation 0, 1, 1, 0, and so on, so sort of the digital logic notation. If you think of these things as computer code, like digital computer code, what this really means is that these states here constitute quantum digital code that is completely legitimate, completely natural in a quantum system, but does not exist in a classical system. I cannot put 2 bits of my laptop here in this code. You just can't do that. But it's very natural in a quantum system. So these entangled states, from the point of view of quantum information, constitute additional usable quantum computer code. And then the job of the quantum software developers is to use that to our advantage. All right, now I'm going to give you, okay, so this is the sort of thing that, you see in the news, oh, Einstein didn't believe it, is spooky action at a distance, entanglement is weird, and people ramble on about it. There's actually something we have done in our own lab. We were not the first to do it, but we were the first and still the only to do it in silicon, which is to look at Bell's inequality. This really unveils the profound nature of quantum entangled states, okay? And I'm going to spend a little bit of time discussing this. So let's say you have two, people, two operators that are typically called Alice and Bob, A and B. And each one of them has a spin. So the spin could be down or up. Now, I'm sorry if this confuses you. For the purpose of this mathematical proof of Bell's inequality, we're going to call, instead of 0 and 1, we'll do -1 and +1. But it's the same thing, okay? So we'll call spin down -1 and spin up +1. And Bob, same thing. You'll have a spin that can be -1 or +1. Okay? Now we measure those spins. So Alice and Bob have some measurement apparatus, which could be the transistor that I showed to you before. We know how to make this, right? And there are certain choices of measurement you can make. So you can measure a spin along a certain direction. So you can ask yourself, what's its projection along, for example, a vertical axis, or what's its projection along an axis that's 45 degrees off. That's fine, you can do that. So we're going to call the measurement number 1, the blue one, this, where it's vertical on Alice and it's 45 degrees to the left in Bob. And then there's measurement number 2, which is horizontal for Alice and 45 degrees to the right for Bob. Okay? But remember, each one of these will give you either a +1 or a -1 when you do it. Okay? All right, now, let's do the following experiment. We measure some combinations of blue and red sort of projections of the spin. And then we calculate this quantity that's called the Bell signal. That is A1, B1, so I've also color-coded it for your ease. So you measure both Alice spin and Bob spin along the blue axis, which are different in both, but I color-coded them in blue. Then you measure Alice along the blue and Bob along the red. Then Alice along the red and Bob along the blue, and then both along the red. Okay? Now remember, all these things are either +1 or -1. That's very important. Now you can rewrite this equation. You can group the A1 term. So you make A1 that multiplies B1 minus B2 plus A2 that multiplies B1 plus B2. Okay? This is not too much, I hope. All right, now, important point. This can only be +1 or -1, each one of those numbers. So let's put in some examples, okay? So let's say we got +1 for A1, +1 for B1, +1 for A2, and -1 for B2. Okay, let's just put the numbers in. So here in this bracket, we got B1 minus B2. So we got +1 minus -1, so that's +2. Then we've got B1 plus B2, so it's B +1 plus -1, so that's a 0, so this thing goes away. And then at the front, we got A1, which is +1, so that's +2. We okay with this? Yeah? Okay. Let's give another example just to, really hammer it on, okay? So we got +1, +1, -1, +1. So first bracket is B1 is +1, B2 is +1, so this goes to 0, so this thing goes away. Then we got B1 plus B2, that's +2. And then there's A2 at the front, that's -1, so this becomes -2. Okay? Now, I could go on like this, for another 5 minutes until I exhaust all the possibilities, but the whole point is, whatever you do, obviously, this number here can either be +2 or -2. There is no other way. We okay with this? Good. So Bell's inequality simply says that if you repeat this thing over and over again, with whatever sort of combination of states and measurements you want, and then you average the results, what you get will be some number that's between +2 and -2. Yeah? What do you think? You convinced? Good. All right. So if we go to the lab and we prepare our nuclear spin and electron spin in an entangled state, and we do exactly this experiment, we find numbers that are well above 2. You see, this is 2, this dashed line here, and there's statistics here, you need to take histograms. But anyway, the best number we got was 2.7 plus or minus 0.09. So this is many standard deviations above that +2 limit. So how does that work? The way it works is this, is that when I was fooling you. When I told you that this can only be +2 or -2, I was making a lethal assumption that you cannot make in quantum mechanics. I was assuming that when I measure, for example, A1 like this, when B is measured along the blue, and then I remeasure it like this when the B is measured along the red, the result would be basically the same. So that whatever happens at this end doesn't care about what happens at the other end. That's not true. Quantum mechanics has what unfortunately people call the spooky action at a distance, but anyway, besides the words, what it means is that if you have, to violate this inequality, you need to have entangled states. So if you have quantum entangled states, you can separate out those particles, and you can separate out by a long way. And if you measure these statistics, you'll find that there is some non-local correlation. What you do at Bob's end affects the statistics of the measurements at Alice's end, even though they might be outside of each other's light cone. Meaning information cannot travel, even at the speed of light, from one to the other before you've collected the measurements. People have actually done experiments where this is rigorously proven, like with labs that are separated by kilometers from each other. So what it means is that you can't just do this operation here and say, oh, A1 and B1 minus B2, because A1 has a different value depending when you've measured it in this case or that case. And then when you work it all out, you'll see you can beat this number. But this shows that there is a non-local correlation between quantum particles. Okay. We have done it in our own device. Now, in this case, of course, the electron and the nucleus are on top of each other, so there's nothing particularly spooky action at a distance. But the reason why this is still very impressive is because violating Bell's inequality is sort of a show of brute force of precision and control of your quantum system. If you ever try to do this experiment, you will find very quickly that this number may probably most of the time be close to 0. You need to have basically 99.9% accuracy on every single operation you do from beginning to end. If you start to take some errors here and there, this number drops down below 2 and you cannot prove you've made entanglement. So this is why this number is important. It's a technological tour de force, if you wish. All right, so this is all about one atom, okay? Now, of course, if we want to build a quantum computer, we need more than one atom, even though it's got 2 qubits in it. And so our next big game is a new type of qubit that we have invented and patented. It's called the flip-flop qubit. It's got a cute name. It's called like that because instead of encoding information in, for example, the state of the nucleus or the state of the electron, we encode it in the combined state of the electron and the nucleus. So the two logical states that we use for 0 and 1 are electron down, nucleus up, and electron up, nucleus down. So it's called flip-flop like that. And the way to operate this is actually by modulating, oscillating the interaction between the two that depends on how much the electron is wrapped around the nucleus. And so in our nanoelectronic device, we have the ability to apply extremely strong electric fields that can distort the shape of the electron, and so we can actually modulate the electron-nuclear interaction and control the quantum states of this flip-flop qubit. In addition, it's very important, we create an electric dipole. So we are displacing a negative charge from a positive charge. So this is an electric dipole. Electric dipoles create electric fields that go a fairly long distance. So our big vision for the future is a quantum computer like this, where we have these phosphorus atoms on a two-dimensional grid of about 200 nanometer spacing, which is ideal for modern classical computer manufacturing technology. And then we can choose which ones we want to entangle with each other just by pulling the electron up, at which point they talk to each other, they entangle, and then we can pull the electron back down and everything stays quiet there and it can survive for a very, very long time, as we've shown to you before. All right, so this is my inroads into quantum computers. So until now, I've just told you we can, encode digital information in the states of certain quantum systems, such as spins. I'm going to say a few more words about, why you want to do that. I'm not going to spend a lot of time on it, but just a few. And also to hopefully elucidate what is really the deal about quantum computing. So this is a classical computer, okay? Just classical digital code. Let's say you got 3 bits. With 3 bits, you can write 8 different binary numbers from 000, 001, blah, 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 all the way down to 111. So that's all the numbers from 0 to 7. So you have 8 numbers, but in terms of information content, you have 3 bits of information. That's, bit number 0, bit number 1, and bit number 2. So I give you 3 bits, and I can define 1 out of 8 numbers. Now, if I do the same thing with quantum bits, for example, the spins that I've shown to you before, I have 8 basis states that are the same ones as in the classical case. But now I can make any arbitrary superposition of these 8 states. So I can create a quantum state that is some coefficient times 0, 0, 0 plus some other coefficient times 0, 0, 1 and so on. So now I have 8 numbers that I need to give you to specify what is the quantum state of this object. So before I needed 3 bits, now I need 8 numbers. If I had 4 bits, I would need 16 numbers. So in general, the way it goes is that for n quantum bits, you need 2 to the power n numbers to specify the full quantum state. That is assuming you have the ability to create any arbitrary superposition of all these states, including, I mean, many of these will be some of those entangled states that I showed to you before. Okay? So that's how you get all this extra information. A lot of this stuff is entangled states. It's in computer code that comes from entanglement that you just don't have in a classical computer. Now, what does that mean? So this is an example. It's not the greatest thing, but if I were to kind of give you something more profound, then we kind of get lost in the big things of the universe. I'll give you the simple version. In the universe, there is about this many particles, like electrons, protons, neutrons. Okay? 10 to the 90, so it's 1 with 90 zeros after that. Now, 10 to the 90 is about the same as 2 to the power 300. Which means that if I had 300 quantum bits that I have the ability to fully entangle, I can make any combination I want of all their states, I would need as many numbers to describe their quantum state as there are particles in the universe. So this is the thing that people often use to give you a sense of how exponentially large is the power of quantum computing. But there's a big caveat. This is only true if you have the ability to create an arbitrary entangled state of all the spins in there. Because, for example, in every covalent bond of every water molecule or every other molecule in your body, there is a pair of entangled spins. But they're only pairwise. So my water molecule on this, sweat here on this side of my finger has got a pair of entangled spins. There's another sweat molecule on the back of my hand that's got a pair of entangled spins, but I can't entangle this one with that one, right? So this is only true if I can entangle everyone with everyone. And that is actually really, really, really hard to do. Unless you do something very clever. So how do we get there? This is the sort of, cosmological example which people talk about in the news. Let's do something a bit more practical. And this is something that you will probably hear about. You may have heard about it already if you follow the field, and I'm sure, within the next year or so, we will have the big splash from someone. Something called quantum supremacy or quantum advantage. Some people are sensitive to the word, but anyway. No, it's true, but yeah. It's now kind of part of the common language. So let's say you have 50 qubits. Let's take modest. 50 qubits, you need 2 to the power 50 numbers, which is about the same as 10 to the 15. And let's say you use 1 byte for every number. That is a petabyte. So that's basically 1,000 terabytes. And this is something you can kind of picture in your mind. You know what a terabyte hard drive is? It's just a little rectangle like this. It's about the size of your mobile phone, maybe twice as much. Imagine 1,000 of them. You can stack them up here on the stage or make a little stack. That's a petabyte. Okay? That's how much you need to describe 50 qubits. Now take 70 qubits. Now you need 2 to the 70, which is about the same as 10 to the 21. So that is 1,000,000 petabytes or 1,000,000,000 terabytes. So now you have to imagine 1,000,000,000 of these terabyte hard drives. They won't fit in this room. And in fact, that is about as much digital data as there is on Earth right now. Okay? That's all there is. Take all the hard drives, all the supercomputers in the world, all the mobile phones, all the RAM, all there is out there is about the amount of information you would need to describe 70 fully entangled qubits. So this is now becoming something tangible, right? So if you can do a quantum operation that demonstrably uses all the computing power of all those 70 qubits all together, then you have done something that cannot, even in principle, be done on a classical computer, because you will need all the data that there is in the world. And if you just add one extra qubit, you will need to double all the data that there is in the world. So you can't really keep up with it anyway. Okay? But there is the catch. How do you make sure that you don't get stuck in some little corner with some small subset of the states you can write with 70 qubits? Because that's the danger. Yeah, I got 70 qubits, great. Can you really entangle all of them? Can you really make any arbitrary entangled state of all those 70 qubits? That's not easy. But there are some ideas for how to do it. And this goes back to one of my greatest passions that I think is going to bear a lot of fruits. It already is, in fact. I won't talk about it today much, but it's quantum chaos. So chaos is, at its heart, a classical phenomenon. So the majority of classical dynamical systems are chaotic. This is one example. This is the smoke of a cigarette. It's very non-fashionable these days, but I'm sure you've seen the smoke of a cigarette once in your life. And if you remember what it looks like, it goes up straight for a little bit, and then it goes turbulent. It goes into a kind of cloud. Now imagine you take two smoke particles that come out of the tip of the cigarette really, really close to each other. Right? And so they follow each other's trajectory for a bit, and then eventually their trajectory diverges. And if you wait long enough, you may find one smoke particle at that corner of the room and the other smoke particle at that corner of the room. So the dynamics of those smoke particles is chaotic in the sense that it has some aperiodic, meaning it doesn't come back. You can wait long enough, those smoke particles will not all recoagulate at the tip of your cigarettes. They're going to fill up the room and they're never going to come back to your cigarette. And also there is a very sensitive dependence on the initial condition. A tiny perturbation can give huge difference in the final result. This is also known in the popular literature as the butterfly effect. The weather follows a chaotic, dynamical equations. And people say a butterfly in the Amazons can cause a cyclone in New York City. Just the tiny perturbation of a butterfly flipping its wings can have a huge repercussion down the track. And so if you then look at the mathematics of chaotic systems, there are some fascinating things. Fractals come out of this as well. What it boils down to is that you find these things called bifurcations. And so for example, a dice works like that. Right? You would throw a die, or a coin, even easier. Okay? So you toss a coin, you get a random outcome. Why is it random? It's random because even if you had the most trained, sensitive fingers to toss the coin exactly the same way every time, the problem is the coin has a bifurcation. When it lands on its head like this, it can fall this way or the other way, and it's infinitely sensitive to exactly what you did, which way it falls when you are at that bifurcation point, right? That's why it's random. And then these things, depending on the sort of dynamics that the system is subject to, they keep happening. And so you get these recurrences. So you get a bifurcation here, and then a bifurcation there, and a bifurcation there. And if you could keep zooming in, you would see a self-similarity. This is a pattern. That's how fractals get made, right? So this pattern of bifurcations and repetition at a smaller and smaller scale of the same kind of behavior, to the point that this initial, let's say, trajectory here gets shredded into an infinitely thin set of tendrils that occupy all the space. So that's all cool. It's reasonably well understood in the field of classical systems, and it underpins a lot of the stuff that make our life what it is. I mean, if you want to design an airplane, you better damn well understand how turbulence works on the wings, right? Now, what about the same thing in quantum systems? This is a delicate subject, and it's delicate because, remember the first thing I told you about quantum mechanics is the Heisenberg uncertainty principle. The Heisenberg uncertainty principle forbids you from specifying the position and velocity of a particle to absolute precision. So that means that as I start shredding these, trajectories, I come down to a scale where quantum mechanics tells me, you can't go finer than this. At some point, you hit the uncertainty principle. There's this beautiful paper was done by Korsch and Berry many, many years ago. This is a theory paper, where they look at, I don't want to go into the mathematical details of this. Think of this as maybe a smoke cloud. You just make a little smoke cloud out of your mouth. And, sorry. And, and then you apply some dynamics to, so let's say you got some wind in the room that makes this cloud sort of turn around and pull, turn around and pull. So at every step, you kind of twist and shred this initial distribution. So on the left-hand side is the classical state. You see, you start with this relatively smooth sort of cloud, and already after 2 steps, you see it's all kind of wiggly and it's got these tendrils that come out. If you did it another couple of times, this would be all very fine, shredded apart, okay? Now, the exact same dynamics, as we increase the Planck constant, this is numerical, right? You give yourself the freedom to choose how much the Planck constant is, meaning how much is the uncertainty you have to accept when you observe a physical system. As you make the Planck constant get bigger and bigger, you see that this thing doesn't happen anymore. So the size of this yellow square is how big the Planck constant is on this scale. And you see, this is, when the Planck constant is, 10% of the size of the cloud, you can't shred it any further. So this cloud remains pretty smooth. So this is one way in which quantum mechanics kind of hinders the natural chaotic dynamics of certain physical systems. And so this is another place where you need to ask yourself the honest question, how does the classical world emerge from the quantum world, given that there are these, disconnects between their behavior? So one thing that has been studied a lot theoretically and very little experimentally, because it's really hard to do the experiments, but we are starting to do that in my group, is sort of the fruit fly of classical and quantum chaos is the kick top. So a top is like a spinning top. And imagine you have a stick and you kick it. You hit it with a stick every now and then. What you'll find is that depending on, what's the angular momentum, how fast it spins, and how hard you kick it, and how often you kick it, and a number of, parameters, you get this beautiful, this is called soft chaos. You get this coexistence of regular trajectories where this spinning top kind of spins on a regular orbit like this, the blue ones, together with the chaotic sea. So these yellow dots are like stroboscopic points of where this top is pointing at successive instants in time. And you see, if you start here, you basically spread yourself out all this yellow thing, and you never come back. Whereas if you start in the blue region, you go around in a loop like this. Okay? And in fact, there's a theorem called the Kolmogorov, Arnold, and Moser theorem that tells you that if you are inside one of these regular regions, you're actually robust against perturbation. So unless you do something really major, you're going to stay inside of this regular orbit. So if you start here, you're not going to end up there. Right? You stay inside. Whereas if you start in the chaotic region, you spread all around the available chaotic region. This is well understood from classical physics. Now, what happens if you try and do the quantum equivalent of this? What is the quantum equivalent of a spinning top? It's a spin, obviously. So what we're going to do is to take our beloved, single atom spin qubit in silicon, but instead of using phosphorus, that's everything I told you about so far, we move 2 rows down on the periodic table and we go to antimony. Antimony is down here, it's just 2 rows down. It's got the same electrical properties for every intent and purpose, but it has a larger nuclear spin. It's got a nuclear spin of 7.5. So it's got 8 possible quantum levels. It's a more complex quantum system. And so what we're going to do is to try and recreate the same dynamics that in a classical spinning top gives rise to that beautiful interplay of regular and chaotic dynamics, and recreate that in a single nuclear spin of antimony 123 in our signature silicon nanoelectronic device. So we're going to replace this with our spin 7.5 antimony. So then we are starting to do the experiments. We actually have some very exciting data, but I'm not going to show it tonight. This is some theoretical calculations done by my students and postdocs, where we try to look at the similarities between classical and quantum behavior. So for example, one thing that has been conjectured a while ago already is that when you have a system that is the classical equivalent of which is chaotic, when you do the quantum version of it, it will be very sensitive to perturbation, meaning it will lose its quantum state very quickly. So this is a simulation where you take, so this is the classical map. These orange dots are the chaotic region, and then you get these blue sort of regular orbits around the sphere. This is called the Hammond projection. It's like, you know, those old maps of the Earth where you kind of stretch out the sphere onto this ellipse, you know. Nowadays, you just scroll on Google Maps, but if you got an old atlas, you will know what this looks like. In the quantum case, the classical chaotic region corresponds to regions where the purity, meaning the precision with which you know the exact quantum superposition you've created, decays faster. So this is cool, you know, this is kind of telling you, okay, so I can kind of see where quantum and classical map onto each other. But then you get things that are completely out of this, and this is one of the holy grails for people like us working in experimental quantum chaos. This is called dynamical tunneling. Remember, so I mentioned briefly earlier that there is this theorem that says that if you are in a regular region, so a region where your system just goes around in a periodic orbit, you stay there. Now, so this is again the classical map, and we got a little blue regular region, a regular periodic orbit here. So this is what the classical kick top would do if we prepared him there. It just kind of goes around like this. Now we do the quantum equivalent. Now, the problem with the quantum system is that you can't think of a spin saying, oh, the spin is pointing that way, I prepare it pointing that way. That's not right. The spin has a quantum uncertainty. It's like a blob of probability that can be centered like that, but it will have a smudge around the sphere. Okay? And this smudge is given by the Planck constant. So the real way to describe a spin that's pointing there is actually this smudge of probability here, the bright part, which on the Hammer projection is kind of here. So if these obey the classical dynamical theorems, what you should expect as you let time evolve is that this blob kind of wobbles around where it is, right? Instead, let's see if the video starts. Oh, please. Let me just start that. Okay. Instead, you see what it does? It wobbles a bit, but then it goes to the other side. And then it comes back. Then it wobbles a bit where it was, and then it goes to the other side. And then comes back. Why is it doing this? It's doing this because I am not authorized to say, oh, I prepared my spin over there. No, my spin was there with a certain probability all around this sort of bottom corner of the sphere, which means it had also a little bit of probability of being in the other regular region. And so after a while, it will go and occupy that regular region and then come back. So this is a striking quantum mechanical violation of what's known as the Kolmogorov, Arnel, and Moser theorem. Okay? And then there's another thing which is more kind of, this seems to make more sense, is that if you prepare it with the caveats before, if you prepare it mostly in the chaotic region, so like here, then you'll see, you'll see what happens Come on. Play for me. I was just thinking about it. I should be doing it. All right. It's very exciting, so we can't miss it. Please. No. No. Okay. I'm still loading it. Okay. Let's do it this way. So it was coming. Oh. Okay. Yes. So you see what it does? It spreads itself all over this chaotic region. Now, this is actually a perfectly deterministic process. And as a result of these chaotic dynamics, you end up in a state that is actually highly entangled. So if you were to encode quantum information on the 8 levels of these atoms, you end up, when you're in a state like this has components from all of those 8 states. It's a highly entangled state. And your system does it just by virtue of its chaotic dynamics. So this is in fact, okay, now it's coming. This is in fact an idea that has been put out by our colleagues at Google, who are building some large-scale quantum computer devices using superconducting circuits. This is a 9-qubit device. They presented a 72-qubit device in March this year. And so the question for them is, okay, we can put 72 qubits on a chip, but how do we make sure that we use all of the possible entanglement between those 72 qubits? We make it obey a chaotic time evolution. That will, by nature, occupy all the computational state of the system. It's like trying to fill a whole room with smoke. You just have to make sure that the dynamics of the smoke particles is turbulent. And it will all happen by itself. You don't need to move every particle of smoke by hand to fill up the room. It will all happen by itself. So this is where chaos is having a whole resurgence in the field of quantum information. It's going to help us use all of the entangled states that we can make in a quantum computer. So my grand plan is to keep building these quantum computers using these phosphorus atoms, which have the advantage compared to superconducting circuits of being much smaller. So this is actually what you would see on the naked eye. This thing is big and it's got 9 qubits on this. Whereas the phosphorus atoms, I could put them 200 nanometers apart. So you could put millions of them on a square millimeter. And they also have very long quantum memory time. And at the same time, I've got a project to understand and control and eventually utilize quantum chaos for the purpose of, 1, understanding how the quantum to classical boundary takes place and how and why, and 2, maybe use it for quantum computations. So with this I'm finished. I just want to give you a little summary of take-home messages. First of all, those things you see in the news as being weird and strange and incomprehensible, like superposition and entanglement, are completely natural, and they are resources. They are things you can use. And we are starting to do that. We have some of the best quantum devices in the world made in silicon, which is the material on which also the classical devices are made. So our hope is to interface the quantum with the classical soon enough. If you can blow it all the way up to the scale of a useful quantum computer, you can harness an exponentially larger computational power. And finally, quantum chaos is having a resurgence, both for, let's say, fundamental, almost philosophical reasons to help us really understanding where and why the quantum to classical divide takes place, and 2, to actually help us make better quantum computers. So with this I'm finished. I want to thank all the funding agencies that have supported me over the years and all the fantastic people, many of whom are here tonight, who have been working with me over the years, both junior and more senior people. And thank you all for coming out tonight. I think I've gone a little bit out of time, but maybe we can take a few more questions. Yeah, so there is a microphone there, and if some, okay, question there.
Sorry. Too close to the...
Thank you. This is a question about entanglement, and you were saying that if two, I think, particles are entangled, they could interact even beyond the cone of light, I think you said. Do they first have to be entangled within the cone of light? Is there a minimum distance when you create the entanglement and then you can move them apart?
The simple answer is yes. There is a trick to go around that, but the simple answer would be yes. Let's say the normal way you would do it is yes. You entangle them first when they're close to each other, and then you can separate them out. There. Sorry.
Sorry.
Thank you. I was just wondering if you require power to maintain a state and whether it could have like applications in terms of memory and storage as well as computation, like the quantum states.
No, you don't require power. In fact, the key to preserving a quantum state is to eliminate every exchange of energy between your quantum system and the rest of the world, unless you are doing operations. So when I'm flipping the spin from down to up, I'm actually pumping power into it. But once I've done that, I want it to stay there. Okay? As a memory storage element, it has a very fundamental drop. I mean, you need memories for quantum computers, so you make quantum memories. That's a separate part. But you would be really, really not clever to use that for classical memory, for the simple, basic, and profound reason that there is something called the no-cloning theorem, which is that you cannot make a copy of a quantum state. So once you encode something in a quantum bit, you can never duplicate it. And the reason why, actually I'm going to spend 1 minute on this, is one of my favorite explanations. The reason why you cannot clone a quantum bit is actually very fundamental, and it has to do with the uncertainty principle. Let's say I put my spin in a superposition of up and down, 50-50. If I observe it, I can never see that superposition. I only see it up or down. But if I could make 100 copies of it, then I could go and measure each one of them, and I'll find 50 up and 50 down, and then, dang, I've seen that I've got a quantum superposition. But then I would violate the uncertainty principle. So I can't do that. It's fundamentally impossible. There was a question.
Thank you. Thank you.
Is that off?
Should be on.
Should be on. Tap tap. It's on. Okay. I can't hear it, but
Yeah,
oh,
it is now, yeah.
there it is.
Okay.
Like magic. It's a quantum microphone. Thanks, Andrea. Question about computation and programming and actually using a quantum computer. You said that you could encode all the data on the planet on just 70 bits of something.
Quite what I said. I said that you would need all the data on the planet to describe the state of 70 bits.
Okay.
Yeah.
And suppose you want to use that description as data that you want to manipulate. You would use your microwave radiation and so on to manipulate the state of those 70 qubits. Can you, or how do you, tune your radiation so that it manipulates those qubits one at a time or something? Because if what you're doing is, if all you can do is broad spectrum irradiation, then you're not going to be able to do much computing. So the bit I'm missing is how do you then manipulate all this to make it do something?
Perfectly fine question. It's just that I didn't say it. So, for example, take an example like this. Say, so I have figured out what is the exact frequency to, for example, flip the electron spin when the nucleus is down, okay? And I've got 1 million of those atoms. Those atoms are all identical. They all respond at the same time. And your question is, how do I make sure that only this one responds and not its neighbors, right? What I do is I slightly modify with a local electrostatic gate the shape of the electron. At which point, I mean, I should make an animation here. These levels come closer together. So I can tune, like a little radio dial, I can tune the frequency of every individual atom with an electric field applied locally. So this can actually be done. We have actually done the experiment, it's published 3 years ago, where we had a spin that was by default off resonance with a continuous microwave. And then when we want to operate it, we distort the electron and we bring it into resonance. So then it's get an operation and then it goes back out. And you can imagine doing this for as many qubits as you want. One more question? Yeah.
Hello. Just a futuristic question to ask you. So I have an Encyclopedia Britannica at home. It was printed in 1985. If I open up the pages, that's 33 years ago. They mention things called mainframes in computers. In 33 years, I'll be 66 years old. And when I'm 66, are we going to be talking about quantum computers as we do mainframes and the PCs that went in the past? Seeing as right now, they're still not commercially applied. And within my generation, at least, you know, the speed and progress, how do you see it going?
I'd say so. 33 years is a good chunk of time. So I would really like you to see at the age of 66 a big mainframe quantum computer being online. You won't have it in your room, but you will be able to connect to it. So the way quantum computers will be brought to the public will be one where, in a sense, it's already happening. I mean, the majority of the calculations you do in your daily life don't happen in the CPU of your own computer. They happen somewhere on a data server, and you just connect to it. So there will be in the data, centers, there will be one room that's got some big refrigerators like these ones, and you don't even need to know. Maybe you'll know because they'll charge you more. If you want to use the services of the quantum computer, you connect remotely. And in fact, you might use quantum secure communications to connect to the quantum computer if you so wish, if you get optical fibers to your home, which is a different matter. Assuming you do one day, you could connect securely to the quantum computer and get packets of data back and forth where the data is handled by a quantum computer and sent back to you. So you will never actually need to have this machine in your room, but you can connect to it. So I think we need to close off.
My final question is, what would Pollock make of it all?
Oh, I think Pollock, if I can, this is a very wild guess of how his personality will react to all this, but I think he would like this one. I think he would like very much, well, this one as well, but this one especially. Oh, and the Bell's inequality. So this one where I show that we can preserve the quantum state of this little nucleus inside a functional silicon electronic device, and we can entangle it with its own electron and nearly reach the quantum limit. The quantum limit is 2.82, 2 square root of 2, so 2.70. Pollock would probably be very impressed with the squeezing everything out of the apparatus that we've done to actually achieve this result.
I think with that, Andrea, I'm going to give a short word of thanks. It's going to be very short. Andrea's given us a wonderful, I suppose, exposition of essentially the whole world of quantum mechanics moving into quantum computing. He started off with the Heisenberg uncertainty principle, which I remember from when I did university physics, and that's when I started drifting off. But I didn't tonight. Then went on to qubits and then quantum oscillations and the whole idea of quantum entanglement and how it led into quantum computing. But what I really liked about Andrea's talk, because that's basically, I think, where Bryn and I have stopped when we've listened to your talk, so that you then brought in the whole concept of quantum chaos. I think it was sort of essentially throwing down the gauntlet to Justin Trudeau to say, listen, see if you can do that one. but Andrea managed to do it, and I really like bringing it back to Pollock, because basically I think I got this right, because one of the things which came in that Nature paper which explained his life was something along whatever the apparatus, you need to get the most out of it. And that was what the quantum chaos was doing. It was saying this is how we can get the most out of quantum computing. So could you please join me in thanking Andrea?
Thank you all for coming tonight.
Now, there was one thing in Andrea's talk which I really liked and is very important to the next part of the evening. Basically, one point that you made is when presented with two equal choices, don't choose, just take both. Now, we've got drinks, and we've got white wine, and we've got red wine, and we've got different canapes. So when you're up there, don't choose, just take both.
The natural choice.
Thank you very much, everybody.